Good morning, good afternoon, good evening. Thank you for joining again. CSM Explained. This is our fourth edition, and we're going to be presenting to you the discussion of measuring voltage in e-mobility. Again, my name is Tom Dorr. I'm the Director of Business Development and Marketing here in North America. If you're joining us from around the world, especially perhaps if you're a football, soccer fan in England or Germany, we really appreciate your attendance right now. Maybe you've got something playing on a different monitor that you're paying attention to that game. But we appreciate you being with us today. I'm going to be presenting the beginning and the end of the material today. I'll be co-presenting with Paul Van Opem. He's the president of CSM Products Inc. here in North America, and he'll be taking us through some of the more technical slides and answering questions at the end. So again, we're going to be discussing voltage measurement and e-mobility, and really this could take such a broad spectrum because in reality anything that we're measuring really is a voltage or perhaps a change in millivoltage. Okay? Is the foundation of measurement technology. For example, maybe you have a thermocouple, and that change in temperature comes through the sensor as a change in millivolt that then gets interpreted as a change in, say, degree C or degree F. Maybe you've got a strain gauge going across a Wheatstone bridge, and again, we're measuring that as a change in voltage across the bridge that then gets changed and represented as microstrain. Right? And this goes on for accelerometers as well, and really any other sensor outputs a change in voltage. However, when you get into vehicle electrification, and what we're going to be talking about primarily for the next 20 minutes or so is really the direct measurement of that voltage or a working voltage in the electrical system or some of the main components in the electric or electrified vehicle. So we'll be talking about really what is voltage, where do these working voltages be measured on the vehicle, and what are the appropriate tools and offerings specifically from CSM, of course, for the different applications and selecting the right measurement module for your application, or a combination of them depending on what your use case and test is. So without further ado, let's get started here. And one of the first things that we want to mention is really that there's a growing number of standards and guidelines and regulations that are emerging as to where and how voltage should be measured in an electric vehicle. But some of those applications are really throughout the whole electric vehicle electrical system or architecture, and one of the primary things as an emerging ISO standard is in the measurement of ripple through the system. We'll explain that a bit later. The other is in the high voltage isolation monitoring, making sure that the high voltage environment and the low voltage environment don't have any crossover and create a dangerous situation to the passengers or anyone else that might be touching the vehicle. Right? And associated with that isolation monitoring is, should there be the need to cut off the high voltage system either in some kind of a accident situation, first responders, that whole system needs to shut down and be isolated, but also perhaps in a recuperation or a regeneration. Now that we want to take and recharge the battery, we have to make sure that those systems cut off and that the voltage and current flows back to the battery. So there's cutoff mechanisms, and those need to be measured and make sure that they're performing accurately as well. The whole powertrain system for proof of performance. Does the vehicle have the ride characteristics that are desired? Right? Are you doing some 0 to 60, trying to set new quarter-mile records, or you have a more luxurious experience in ride and feel of your powertrain system? And of course, as we now call consumption tests, really get into the range per charge, the efficiency of the whole vehicle and the drivetrain system to maximize that range per charge and alleviate some of the consumer anxiety in comparison of how far they'd be able to travel before recharging. And then speaking of recharging, also the different component tests, the charging characteristics, trying to charge as fast as possible, and so many other electrified components that they're working as efficiently as possible as well. All right. So with that overview, I'll pass this over to Paul, and he's going to take us through some of the details, building up what is voltage and different ways of measuring that.
Well, thank you, Tom. Good introduction to the different areas within a vehicle that we need to measure voltage, as well as all the different sensors that we do measure voltages. So I am Paul Van Opelm. I'm the president for North America for CSM, and I'm going to go into hopefully a very simple, easy exercise of what is electrical voltage. We start off with electrical voltage as maybe two different points, or in this example, we're showing two boxes where we have one box that has positive charges in it, and the other box has negative charges in it. If we were to measure something across that, let's say if we were to check and see what that voltage is, you would see that these separated charges develop a voltage that is between them, or a potential that is different between them. This is just 2 points in an electrical field and have different potential voltage levels, if you want. When you have 2 points which are separated or isolated from each other, and then you electrically connect them with some type of device or wire or conductive material, that then ends up being the ability to transfer that electrical charge between the 2 points, thereby creating current. So they can very easily become a current source. Okay, the electrons will move from positive to negative, and you'll start seeing current flow is created in this type of environment. So everything that you put into this then as a potential now becomes a flow or acting type electrical means. So how do we measure this electrical voltage? There is a need to have 2 different points. You really are looking for 2 different points. So in this example, we have 2 boxes. Again, they are isolated, so there's an isolator sitting in between the 2 parts. You can essentially consider this a battery. Could be high voltage, could be low voltage, it really doesn't matter. But you have 2 different points with an electrical potential difference between them. And what you want to measure is, what is that electrical potential difference? You can put something between them, some type of, it could be a lamp, it could be a motor, it could be anything, as long as it has an ohmic resistance to it. This will allow you to see what is really the voltage drop across that ohmic resistor. We can't change it. It's called Ohm's law for a reason. It's a law. We don't change it. V equals IR. So what we want to know is, what is the voltage drop that crosses that thing? In an ideal world, if we were to look at this in a more realistic world and consider everything that goes into this, you might have a switch in there. You might have connectors. So you have different materials now. You still have that ohmic resistance or lamp, and you still have all these connectors and wire. So all of those type of things end up being a little bit more resistance. Now, relative to the load itself of a lamp, it's very minor, but you do have to take those into consideration or understand them. So when we consider something like this, or we are looking at very deep analysis into this type of stuff, we now have to say, okay, well, I have voltage drops that are happening all the way around this whole circuit. It could be just the material. It could be material changes like in a connector. It could be just the resistance of the wire. It could be a switch. The switch can be wide open where it's infinite resistance. It could be together or connected and where you have material differences now. So all of these items still come in and have an effect to what your voltage is and what your voltage drop that you're most interested in. They usually, most resistors, even a switch or material differences, come off as a thermal type loss. So when we look at a weld stud, maybe a body weld stud, is everything has to be thought of, including that weld stud is a material change. And often when they put these weld studs, they paint them, and you have to use special type nuts that are cutting nuts that cut through the paint, but it still develops some resistance in there. We don't want to get not take into effect some of these other things that play into the actual voltage across the load. So now when we go to measure these, we do look at everything that can affect the circuit, and that includes your measuring devices. Your battery voltage itself is one piece. Switches are a different piece, materials. Well, so is your measuring device, because what we do is we put a very high resistance across 2 points within this circuit to measure the voltage. So on this switch, when it's open, we have an infinite voltage. When we close it, we will see a very small voltage drop that's relative to the material that it represents. So idealized, we aren't as interested in that one as the switch as we are the actual lamp load. So we sometimes just say it's negligible and we can ignore it. But in the real world, we have to be concerned about any thermal type of impacts on these. So your voltage went from an infinite or a 12 volt full drop on the switch when it was open here, to now the 12 volt drop is across your lamp, because we're taking the flow of this current down to the lamp, and now it's connected to the negative side, which will be your base ground, and you get your voltage drop across only your lamp. Again, switch, connectors, wire, we really think about, we have to be cognizant of it, but we don't consider it the most relevant piece of information. So voltage measurement devices should have a really high internal resistance. This is required for the purposes of knowing that current always takes the path of least resistance. So we want those resistances in the voltage measuring devices to be as high as possible. You want to make sure that you don't have any effect to the system being measured. That keeps you from having incorrect measurements, or maybe not knowing exactly where your thermal loads are going to happen, and being very cognizant of the whole system and knowing that your device has the least effect to your measurement. Okay, so now we're going to talk a little bit deeper. Most of the stuff we were just talking about was DC voltage. This is now an introduction to all the pieces of voltages that you could have. DC, AC, AC with offset, and DC voltages with AC components. And that's where, as Tom had mentioned earlier, where you're going to. Here we have a very simple voltage measurement that's at 4 volts DC continuous. And we are just showing that the 4 volts has no issue whatsoever, being continuous and very steady on a scope meter. Now we want to look at an AC voltage. AC voltage has a sinusoidal type wave. This sinusoidal type wave has a certain frequency. This one happens to be right around 6.1 kilohertz, but it has a peak to peak of half a volt. Or excuse me, peak to peak of 1 volt, half volt nominal amplitude. So now we're going to look at AC voltages with offsets. These are where you have that same type of AC component, but now it's offset by some DC factor. We just took the 4 volts that we measured earlier along with our 6.1 kilohertz AC voltage measurement or supply and combined them together. So now we get a AC voltage offset of 4 volts. We're still maintaining the same AC components in there along with the amplitudes, and as well as your zero line is now at 4 volts for that AC component. Now DC voltages with AC components. This is what a lot more applications that you see out in the field will have, where you can have a very clean DC right at your first step, and let's say something turns on and you start seeing consumers use up that voltage, it'll dip. If you're in a vehicle, your alternator battery will try to buffer this and then bring you back. But you're seeing quite a few AC pieces in this DC voltage. So this is a fine example of where you might see some ripple type events. Okay. You have to be cognizant of how fast these ripple events are and know that that speed or getting into those components of the AC, you have to collect at a speed and at a frequency that will be good enough to reproduce that signal after the fact. So with an engine standing still, we start up the engine, we see a 12 volt signal, we see the voltage overall dip down, and after combustion of the engine, we see the alternator and consumers such as ignition system give these feedbacks in the after starts phase, where you're starting to see the consumers are still having effect on the DC stability of that voltage supply. So again, if you want to do good analysis, you'll need high-speed collection of this such that you can collect and have all the information for your AC component to analyze. So different voltage systems that we have out there and how fast we have to measure. There's 12 volt, 24 volt, 48 volt, 400 volt, 800 volt electrical systems out there for drive as main drive pieces, as well as just ancillary drives or components within your vehicle. A radio or even the controls for an AC and stuff need a 12 volt signal input. So despite having this big battery with a lot of ability to do what you need it to do, all of these consumers start hitting the battery and you start seeing various AC frequencies and mixtures in there. Okay, again, need to have the high data rates to capture those and be able to get all those pieces identified for analysis. Okay, so what should we consider for the voltage measurement? With all the different components, you need to know your DC, AC, DC with AC components, and understand those before you select your measurement device. Different voltmeters have different uses. Also understand what your environment is. Are you in ultra low voltage, less than 60 volts, or are you really what they consider safe, high voltage environment, and being safe in that environment? So we've used data capture rates as low as half a hertz, could go all the way up to 1 megahertz. Expected ranges, make sure you identify them along with if you're in the high voltage or low voltage or ultra low voltage or extra low voltage environment. Also understand in certain countries, there's laws in certain countries who can and who cannot play with these. So very good to keep that into consideration. Who can install them, who can measure. So again, voltages above 60 volt DC or 30 volt AC is considered important items to protect yourself from. Follow we have guidelines out on all of our devices. You should follow those guidelines and also understand your local rules and laws for each environment. Here's a fine example, same signals that we were working with. A multimeter can measure both these signals. Obviously, 4 volt DC offset, and then we have a true RMS AC component in there, which would be 0.354 on a half volt nominal or a 1 volt peak to peak signal. So multimeters can be used very easily this way and display all of your necessary information that you might need. Benefit of a voltmeter or a multimeter versus the raw acquisition is, yes, those same components of plugging a multimeter into an outlet, getting your voltage, DC voltage offset, and your RMS calculated AC component. If you were to collect in actual data acquisition, you'd see that this signal is actually over about 320, 325 volts as the actual raw signal that goes in. So you got a lot more information here to work with for further analysis when you collect it with a true data acquisition system. If you're just using multimeter, you have some challenges in there. You have to back calculate and do everything else. So we did a little test with ours where we took our high-speed acquisition module right here shown, and we brewed a cup of coffee with a coffee maker over in Europe, and we were able to show the actual true voltage dips and continuous DC pieces of your voltage DC, max voltage, min voltage, peak to peak, if you have a DC analysis relative to the two pieces, as well as an RMS if there's the AC components in there. And we were able to see that 321 volts, which is a decent peak to peak or max voltage. And if you do that peak to peak, it doubles up pretty close, okay? And your actually DC offset is very minimal. So it followed what we anticipated, and we were able to get the entire signal for this analysis and do deeper dive as necessary. Okay. Again, a voltmeter could come in and do similar type measurements, but you're only going to get the true RMS value, which is our bottom one, and your DC voltage offset, if there is any DC offset. And here it's only 0.024 volts, and it's very minor. Obviously, having two different measuring devices at two different times gives you a little bit of a different result, but that's okay. They're very negligible. But you don't get your min, you don't get your peak to peak, and you don't get your actual max out of that. Okay, with that, I'm going to turn it back over to Tom, and let him go through more of our modules that would be used in all of these environments.
Thank you, Paul. I appreciate the technical assistance there. And as you said, I'd like to quickly go through some of the different measurement modules available from CSM and some of their different use case applications. I think many of our customers online and what CSM has been known for in the marketplace for over 38 years here is really our low voltage applications and measurement modules, whether that's sampling on a CAN bus or at high speed on EtherCAT, as you can see the two modules here. But these are really intended for the ultra low or low voltage environment. When we say ultra low, this is really in the millivolt range where you're detecting a change in some physical attribute as detected by a sensor, as I mentioned earlier. Or you could take the working voltage up to 90 volts. And if you're doing that, as Paul showed in the coffee maker example there, just how fast that some voltage can drop and spike and then settle down with AC components in it as a device is doing its task, even if that's a coffee maker or a battery thermal management system on a vehicle. They all perform very similar. So you need very fast sampling rates of that, and we can do that in the EtherCAT bus with up to 1 megahertz sampling rate. And we're known for our very rugged and compact IP67 form factors for those modules. Now, getting up into the range of, I believe I missed the slide. No, I didn't. I'm sorry. Okay. So getting into really measuring that direct working voltage up to 1,000 volt, and that is for continuous voltage. We can actually take peaks up to 2,000 volts. We have the product line, which is a little bit different because of its use of the high voltage safe connector cable. So you'll see that we have a different connector here for the sensors to be, or the sensor cables to be plugged into the module. They still work on either EtherCAT or CAN through a LEMO port. And they are also IP67 for the EtherCAT module and the mini module format, or we have a module for CAN in this test bench format, which is IP65. But the key thing about any of these products, and you can learn a little bit more about this in our first CSM Explained on measurement and high voltage, is really the safety factor. Having a safe measurement chain all the way from the measurement point, whether that's direct measurement of the voltage or through a sensor, through that cable into the module, and then having the reinforced isolation from channel to channel to communication port bus, whether that's CAN or EtherCAT, and from channel to the power supply, so that we don't have any of this dangerous high voltage and current getting passed through any other measurement instrumentation, the laptop, or someone who might make accidental contact at the end of a connector while they're doing the installation, or even hands on the keyboard and there happens to be a crossover there. So these are all certified for that isolation barrier with a unit test that we supply in addition to the calibration, where we actually test that isolation barrier up to 3,100 volts for 5 seconds, and it's rated much higher than that. So we're 100% safety testing all of these modules before they are delivered to customer. All right. Now, often the measurement of voltage is not just voltage, but the use of voltage when combined with current to calculate power. And there's multiple powers: instantaneous power, reactive power, et cetera, doing any kind of efficiency analysis where there's power in and power out. And so through kind of evolutionary and innovative work with our customers, we have the breakout modules that not only measure the voltage at up to 1,000 volts, but also simultaneously measures the current in the same location. It's safety sealed inside of the breakout modules. They're also IP67, and again, the same safety concept and reinforced isolation inside the module for the high voltage safety. So these breakout modules really, as I said, they're not just measuring voltage, but also current and doing power calculation. And they are installed directly in the high voltage power lines of the vehicle. And I'll show you some examples of where those measurement points could be in a use case, which gets us to a discussion here on some of these applications. So measuring this ripple or this AC component and feedback of different interactions between components on a vehicle is a great use case where you need to measure the voltage. So all of these components on the vehicle, not just the inverter and the electric motor, but your air conditioning and DC to DC converters to go from the high voltage environment to low voltage auxiliary components, your heating system, these all have individual electronic components in them. And if we look at something as simple as a coil here, we not only have an inductive element, but there's also resistive elements here in the copper and the resistance in the copper. And so we end up with a conductive element. And when we put some of these components very close together to each other, these conductive elements really create a electromagnetic field and can induce voltage onto other nearby components. And they not only are putting a ripple back through the electrical system based on their internal switching and consumption of the power, but also influencing each other. So often you need to be able to measure from device to device and what kind of effect this is putting back into the electrical system. So if we look at a simple block diagram where we have a high voltage battery in the center here with consumers of that power or energy throughout the vehicle. Maybe we have multiple drive motors in our powertrain. We have an onboard charger that's going to be providing the charge into the battery. DC charger on the other end, as I said, DC converters, your AC compressor, heaters, etc. All of these are consuming the energy, and they're also providing a ripple back into the system. And how do they influence each other? And this is a great example of where customers have applied our high voltage breakout modules, multiples of them, upwards of even 15 of them on a vehicle, to optimize the performance of each of these auxiliary consumers, but also then to optimize the overall electrical system, and primarily make sure that the powertrain performance and vehicle range is as expected. The component tests, looking at a electric axle. Here's an example of the requirement of really needing high speed measurement. So here's a standard road test, and we can see with the current here in the red line, right, as we're accelerating and coasting, right, and then even in a regenerative mode here, where or recuperation is another term for that, popular in Europe. Regeneration is where it's less than zero, so the current is recharging back into the system. But looking at the voltage, if we zoom in very closely down here, we see that we have these very fast and very large voltage peaks. So we zoom in a little bit farther here, now going from a 20-minute drive cycle to looking at just a few seconds of what's happening in here. We can see that we have a major drop and minimum voltage here of 355 volts. That's too high of a ripple. With the new ISO standard, that would be deemed not acceptable, and something would need to go through a design change and a performance improvement. Right? When we're looking now at this really closely at 32 milliseconds, we can see exactly what's happening in that change of voltage simultaneously with the current, because it's being measured at the same time together in that breakout module. And you can see, to really understand what's happening in the voltage signal, you need sampling rates that are well beyond 1,000 kilohertz, even up to the maximum that we provide on the Ethernet bus, EtherCAT bus of 1,000 kilohertz or a megahertz. So in the charging system, this is another good example. Part of the transition, Paul was talking about taking measurement from the power outlet, right? So from the infrastructure, from the utility supplier to a coffee maker. Well, what's happening really in that dirty signal, if you will, and what is the power that's being supplied from the infrastructure to a charging station, from the charging station into the combined socket here, on the onboard plug-in for the vehicle, and how much is actually then getting to the battery. So looking at power efficiency and voltage drops through this system at 3 different points can easily be done with those breakout modules as well. Okay. We mentioned the high voltage isolation and monitoring. Here's another example where you can use our high-speed EtherCAT module. Now we're not also concerned here about any power analysis with current. So if we just want to look at voltage, maybe between the battery and some additional consumers, if this is the air conditioning or heater or DC-DC converter, we could instrument between the battery and that high voltage cable a simple little measurement box where we would have the high voltage plus the minus, the high voltage plus to the vehicle ground, the minus to the vehicle ground, and even the cable shield to the vehicle. Basically, in summary here, the CSM modules for very low voltage to standard low voltage or 90 volt measurement applications are our typical CAN and EtherCAT modules. We have for the high voltage, again, being able to measure from 1 to 1,000 volts or 2,000 volt peaks in there. The high voltage product line here that is all encompassing our or consistently incorporating our high voltage safety concept to have a safe measurement chain from the measurement point all the way through the communication bus. And finally, doing the same thing here with the breakout modules, that not only measuring voltage, but simultaneously with current for doing that power calculation and keeping everything at high speed synchronization. So thank you for your attention today. We appreciate your involvement.